Welcome back, everybody. So we're right in the middle of this conversation about normal stuff. We did something real quick last time. We'll repeat what we did, but there were some questions. What's the conjugate prior? Which prior do we use? What's this flat prior? And that's not a 2-second conversation. There is a long conversation to be had about that, and I'll try to spread that conversation over a few different examples so that we don't do it all at once. But I'll be repeating myself often about important characteristics of priors. What does it all mean? What do Bayesians actually do? And how do you think about it? And if I were more of a rigorous Bayesian, I would say there's a correct way to think about things. But I think that there's like 10 different correct ways to think about things, and I don't care exactly how you think about it so long as you do the right thing. So, but there's different explanations, and different people will appreciate different explanations when you're telling them about Bayesian analysis. Let's just jump into the example and get back to it. So keep in mind, we're sampling from a normal distribution. Normals look like this, right here. I changed my random variable over here to z, but it's the same shape. So we're sampling something from this. I'm just calling the realization x1. So we get one data point from that. And there's a few questions we could try to answer. So what's the posterior mean? We did a really quick analysis on the posterior mean last time. And what we need to do to find that is we take the likelihood and we multiply it by a prior. Since mu is the only thing we're trying to infer, because somehow the hand of the statistical gods came down and handed us sigma, so we're going to condition on it. That's not totally unrealistic. There are people that operate that way. So if you're an engineer, all your time might be in the workshop making sure your machine that you're using to measure things is within some tolerance. And they might spend all their time making sure the machine is calibrated right before they go and use it as a measuring tool. And so they might be calibrating in knowing what sigma is and plugging that in a case like that. Of course, if you just see data and you don't have control over all the mechanisms and something like that, you would need to infer what sigma was. If you wanted to do, this always seems a little bit more artificial than that because people teach this a lot in Stat 101. What's the mean given you know sigma? We could ask another question, what's sigma given you know the mean? So, I think this is a really important question. I've never seen anybody just do this. I will tell you, this is called the full conditional distribution on mu. So it's mu given everything else. So it's mu's full conditional. We'll be using that lingo later on. This is sigma's full conditional. Sigma squared conditional on everything else. When we get into give samplers, you'll be using these full conditional distributions. So give sampler is implemented using full conditional. So while it seems like what I'm doing is a little bit of a waste of time, why don't I just jump to the joint inference? You will be using these in practice. But I typically think this is a more interesting question than this right here. What's the mean? So given you know the variance. I think people never know unless you're in this well-controlled environment where you can control sigma and calibrate a machine. I think sometimes we know what the mean level of things are, but we don't know how variable they are. And that's, for me, usually the most important question, how things vary. So let me give you an example. Climate change, whatever this thing is that we're talking about. So people talk about everything warming 2 degrees, and if we hit the 2-degree mark, we're in a lot of trouble. It's not actually that it's just getting warmer, it's how variable everything is around it. So the variability on everything, and I want to know about that variability. Take epidemiology, COVID, for example. I'm not interested necessarily on what the base rate of the infection is. I want to know how variable it is in my environment. So I've added another layer of strata to it. So I care about the variability of things, how much they're changing. So I tend to think that quantifying variabilities is the most important thing a statistician does. So saying that, we like talking about means because they're on a scale that we're familiar with. Anyway, both of these things are important, And we could also ask the question, what's the joint relationship between these? And I'll just point out to you, these are not independent of each other, sigma squared and mu. And all I have to do is go and look at where mu and sigma squared come up in a normal distribution and note that I can't factorize those apart from each other. No matter how hard you try, you'll never untangle sigma squared from this mu. It's always going to be right next to it. You can't factorize it away, so they're dependent on each other. And that might not be something you've ever seen before. So typically in a stat inference class, you'll learn about x bar and s squared. And if you were a so-called frequentist, or you wanted to know about asymptotic distributions, x bar and s squared are independent of each other. That's only true for the normal distribution. I don't know if you guys know that. But that's very different from the parameters being independent of each other. So I think there's a lot to be gained right here where you jointly express the relationship of these two parameters. So if you're trying to build a prediction model using x bar and s squared, I can beat you by taking into account their joint uncertainty. So it might just be like by a fraction of a percent. It might not be a lot, but depending on your field, this could be a very important thing to do. So let's first start with that. That's where we were last time. I want to just point out all of these things are just likelihood times priors. So I write down the likelihood model. What does the likelihood model look like? I could just grab at this, the sampling distribution, and plug in x1 right there, and that's my likelihood function, but you can simplify it a little bit in different cases. So the sampling distribution is here. All I need if I'm trying to infer mu is all of the action in the likelihood that's contributed from mu, because we're holding sigma squared fixed. So I can throw away this part. It has sigma. If I want to say sigma squared, I just draw the square root sign over the top. Oftentimes you'll see that. So, but I could just use this part right here. And in fact, this is probably a little bit too much to use as well. I can expand the square, and I can simplify it. It's proportional to this. All I've done is I've factorized out this part. This doesn't have a mu in there. I can factorize that exponent out. So sums in the exponent get factorized out into products of the whole function. And I can just get rid of that other thing. So I just have e to the minus 1/2 x1 squared over sigma squared. If I wanted this to be an equal sign, but I've gotten rid of this simply because it's constant. So everything in there is constant in the analysis. So I could get rid of that. And I could just use this as my likelihood. I'm going to use that, though. So I just want to express to you, even though we write down the likelihoods, it always looks like the same formula. They can be simplified in different ways depending on which variables you're using. So if I were trying to do inference on sigma, or sigma squared, I need that to appear. So I can't throw away this first part. And I'm going to have a sigma squared in every term here. So when you expand out the squared, sigma squared's everywhere. So I can't throw any of that away. Same thing here, I would use the same likelihood function here, just because I can't untangle the sigma squared from the mu's. So I can't factorize any of that away and throw it away. So I would use the same expression of likelihood for both of these analyses, but they would be a little bit different in terms of the priors that I'm using right here and how I'm thinking about things. In this relationship, I'm quantifying the joint variability between the variables. And in this relationship, I'm quantifying the variability in sigma squared, so the variance of the variance or the probability distribution of the variance, given that mu is fixed, so they're different. So Bayes is always the same game. Write down the likelihood, multiply by the prior. And then you have to know what all your properties are. Of course, as we get into high dimensional land, we won't be able to do everything analytically, so there's another computational layer to all of this, and we'll get into that soon enough when we study Gibbs sampling and Metropolis Hastings and all those good algorithms. I just want to point out, just aside, if I had a normal distribution, if you showed me this and you asked me what the mean and the variance is, in terms of a sampling distribution, I'm calling the sample space Z. There's nothing here that has to do with z, so this is a normalizing constant. If I think about this in terms of the likelihood function, this is not a constant. And so it's with respect to which variables are things constant. So oftentimes I'll call this a normalizing constant, but then you'll say, well, your constants aren't very constant when you upgrade them to likelihood functions. So a lot of times I'll change the lingua, I'll call this an integrating factor. So it's the thing that I use if I integrate over z here, it's the thing I have to divide by, so all of this adds up to 1. If I asked you, what is the mean and the variance, and I gave you this formula, you would say, oh, the mean's right there, and the variance is right there. And I wouldn't even have to look at this part for it. So all I have to do is look at the kernel of the sampling distribution to figure it out. And so this part, right here, a lot of times, to put it into this form, we would have to complete the square. And I'm going to show you a slightly different way to do it. I'm going to save you about 2 minutes on your exams. So, and instead of thinking about completing the square, we will need that trick later on when we do predictive forecasting. It's not going to go away, so we will see that. But I'll try to show you the fast ways through these calculations as well. Instead of completing the square, I can identify what the mean and the variance are through the expanded version of this. So if I write down just the kernel, and I write down e to the minus 1/2, and I expand the square, z squared, z is my random variable here, minus z times mu plus mu squared divided by sigma squared, I can still recognize where the mean and the variance are. I just have to get used to looking at this just a little bit differently. So let me tell you how I do this. We'll come back to these two analyses later. We'll focus on just the first one first. We'll use this trick in a minute, and we'll use this trick regularly. So it's just a question of what does a normal distribution look like to you, and how do you have to have it formed before you recognize its driving parameters. I want to point out, I can identify the variance very quickly on this. And how do I do it? I look at the quadratic term. So keep in mind, I can rewrite this and get rid of that common denominator and just write them over all their own denominators. Same thing, divided by sigma squared, divided by sigma squared. This might help us to look at everything. So if I look at the quadratic term, whatever it's multiplying against is the inverse of the variance. And that's what it is. So I don't need to have it in compact form to recognize that. So the quadratic term, z squared, is the quadratic term. And what I do to this is I take whatever's multiplying against it and I invert it. So quadratic term is this. 1 over sigma squared is its leading coefficient. So this is the quadratic coefficient. And it's not hard to see, that's the inverse of the variance. So the variance of z is equal to the quad term inverted, which is just 1 over sigma squared inverted. I didn't say divide by, because later when we do this in high dimensional space, there is no divide by a matrix. There's invert the matrix. So same thing will apply when we get to high D analyses. Same trick. So that's sigma squared. So that's what I always do first, is I pluck off the variance and everything. And then I go and I find the mean. And so if I know the mean, then all I have to do is look at, oh, and I messed this up twice. There's a 2 there. I guess I only messed it up once. There's a 2 there. So that's that cross term right there. So I've got this other term right here. When I'm trying to pluck off the mean, I look at that. This is what I call the -2 linear term. Keep in mind in this, I always have the -1/2 factorized out in front. I never change that. I don't care if you like to bring it inside and multiply it all the way through. To recognize everything, you're going to have to factorize it. So I always just keep it outside. So I look at the -2 linear term. And I look at that thing, and it looks like mu over sigma squared. So that's what's sitting here. So it's the mean divided by the variance. If I've done these steps in the correct order, I've already got the variance. So all I have to do is now multiply this times the variance of z, which I just got in the first step. So that's going to be mu over sigma squared times sigma squared is equal to mu, which is the mean. So I'll say it just real quickly and then we'll do it in practice. So quadratic term, I invert it, I've got the variance. That works in high dimensional examples, it works in low D examples. This is as low D as we can get. To get the mean, I look for the -2 linear term. I know what the form is, it's mu over sigma squared. So I multiply that by my variance and I always get my mean. That's a little bit faster than taking the expanded form and then simplifying it through by completing the square. A lot of times you have to add and subtract something, factorize it out, and then complete the square. So we're going to avoid that step, at least for now. Okay, so here's our likelihood function for this analysis. We're going to find this. So this is our goal. And so we left off last time with 2 really good answers. Very common answers. So which prior? So pi mu, there's a couple possibilities. So maybe this is equal to, and I probably should say proportional to, just to be careful. Right here, somebody said maybe 1. This is the flat prior. And somebody said the normal prior, normal on mu. And I'm just going to be specific so that I can identify what the random variable is. It's going to have 2 hyperparameters. So this is the conjugate prior. And we'll see that in a moment. If you can't see that instantly, that it's the conjugate prior, I'll just tell you normals can always be recognized that they're e to the minus quadratic function. That's what kernels of normals look like. And so if I take this prior, e to the minus quadratic function, I multiply it into something, the likelihood has this normal-esque form. It's not a normal in terms of the likelihood. It was a normal in terms of the sampling distribution. So when I multiply them together, I still get e to the minus quadratic form. I know the posterior is a normal. And the question is what are the parameters? I just need to identify the mean and the variance. So last time, somebody said flat. What were you thinking about when you said that?
So I was thinking, if we don't have any like a prior information about the data, and then we happen to pick a wrong prior,
yeah,
it's going to have a lot of like influence in your posterior distribution and posterior parameter. So I would rather start my analysis with the uninformative prior, which is my flat prior, and let the data speak for itself.
Okay, so there was a key word, non-informative. So on mu. That's interesting. So non-informative on mu, and that's because it's flat?
Yeah.
You interpret flat as non-informative. It's okay, a lot of people do. So I'm going to make a quick argument. This is, so sometimes people will call this uninformative or non-informative. It's good psychology. So, oh, I did something that doesn't inform you. Can I use a flat prior everywhere? It sounds like that's like, oh, if flat priors are non-informative, let's just use flat priors everywhere. So, because they're non-informative. And the answer is we don't do that, and things are non-informative in different ways. So it's really, I try to talk people and discourage them out of saying non-informative, because I think there is info there. It just might not be it might be non-informative in a specific way, but that changes for all problems. Let me just show you something. Get rid of that stuff. If I ended up picking my prior as flat, so this is flat. It's flat across the whole real number line. For you that are saying that's not a probability distribution, you're right. So it goes on forever. So if you tried to normalize it, you would get an infinite integral. You divide by that and it's not a probability distribution. People still do use it. And I'll try to explain through the lens of the conjugate prior where it comes from. But I want to just say a few things. So this is flat, that's true. Let's do a transformation. Let's think about what's the implied prior. Implied prior for mu squared. And what I need to do is I just need to create a new random variable. It's called mu squared. So I want to figure out pi mu squared. So I'm going to create some new variable. I'm going to call it v is equal to mu squared. Now we have to be a little bit careful on this analysis because I can't invert this everywhere. So I'm going to make this just really simple, just so I don't have to break this into two probability distributions. I'm going to say we know something, and I'm going to let for now. So let mu be strictly positive. I'll say strictly positive. Okay, so I'm going to isolate my analyses to just strictly positive mu's. If I didn't do this, I need to just break this up into a piecewise transformation, because it's not a one-to-one mapping. So since I've made mu positive, I'm going to restrict myself to one of those piecewise transformations. Okay, so now I can do this. I couldn't do that unless I had the plus minus thing and I'd have to break it apart. It's not the point I'm trying to make. So I have root v right here. This is my new variable. So half power is the way I like to write that thing down. So to do a transformation, if I wanted my distribution on v, so I just called this v, came up with a new variable. To come up with this, I use exactly the same thing I would have done before, where I'm going to take, let me just write down, this is, so I'll say g of mu is equal to mu squared. So just following what you probably were exposed to in your probability books. And so g inverse v is equal to v1 half. And g inverse v is equal to mu. So what we usually do to do this is I take my inverse function, so g inverse v is equal to mu, and that's equal to g mu. And you can do this when you have one-to-one functions. So hopefully you all know how to transform a random variable. Where does this formula come from? Can anybody answer the question? It's the chain rule. So it is absolutely the chain rule. If you don't understand that, ask me in a review session, and I can take 20 minutes and derive this for you and tell you where it comes from. But it is the chain rule. Excellent answer. So this is the chain rule where this term comes from. What I like to think, maybe a more intuitive way of thinking about it, is all I'm supposed to do is take this distribution. Now these pi's aren't the same. This one was for mu, and this one is my new one for v. So I take pi mu's distribution, and I plug in a different version of mu. Mu is v1/2. So I just substitute it in. And you can't quite just do that. You can do that with discrete probability transforms, but you've taken the space and you've stretched it also. So you've morphed that space. So if I multiplied something by 2, I've stretched the space by 2. This is a little bit weirder because I've squared the space, so I've stretched it. Keep in mind with random variables, we're going to integrate over them, and we need to account for how much we've stretched that space. And so the determinant measures that stretched area. So if you remember, I said determinant right here, it's just an absolute value. But if we moved into two-dimensional space, this would be an absolute value of the determinant. So of all of your, the partials that you put into that matrix. We'll see a high D example in a couple of minutes. Please.
I'm sorry, I think I missed something. Why are we working at the implied prior from U squared?
Just to make a point. So I'm about to get there. So I haven't made my punchline. I had to do too much math in the middle. So let me make my point real quick and just work out what this thing is. So this part, all I have to do is look up here. This was the thing for mu. So when I have too many pi's floating around, I'll remind you which random variable that pi relates to. This was flat. So I go to this function, and I look at everywhere there's a mu, and I plug in v1/2. There's no mu's there, it's flat. So this is still flat, right here. This part, right here, is v1/2. So this is going to be 1/2 times v to the minus 1/2, absolute value. So this is going to be equal to 1/2 times v half power. V is mu squared, if you like to think about it that way. So, but the point is, on this, so keep in mind, V is just mu squared. Just written in a different way. Is this flat? This is not flat. So what does that look like? Looks like this. Asymptotes up by 0. By taking out the negative sign, I didn't have to draw the other side. It would have done that as well. You can only use this when your relationship is 1-to-1, so I, just impose that. But that's not flat. So when you say that you impose something on mu that's not informative, all its transformations have shape to them. So I wouldn't call that non-informative. You place mass on mu in a different transform space. So when you think you're placing uniform mass on mu, you are placing mass in non-uniform ways on every transformation of it. So that's kind of interesting. So I could probably appeal to you and say, this makes sense. It feels good and comfortable. But if I came to you and said, instead of coming up with a prior on mu, let's come up with a prior on mu squared. If you ended up making that flat, this thing would not be flat anymore. Only one of them could be flat. If I could do anything, the whole universe would collapse. It'd be like an episode of the multiverse. But if I could do anything in math and somehow it still worked, is I could transform uniformity always into uniformity. That would be really cool. Saying that, it messes up everything. Math doesn't work that way. So this is not flat. That's flat. So I would say in some sense, this shape on mu squared is putting mass on mu in interesting ways. And every other transformation we do will not be flat too. So that's why I just picked mu squared arbitrarily. Could have been any function of mu. And just to say it again, because you put flat mass on a particular transform of everything, and you call that non-informative, in every other transform space, it's going to have shape. And so I don't like calling it non-informative. But there is something there. And so if we think about the nature of the parameter, right here, this is a location parameter. I think I called it a shift parameter last time. So it slides the distribution to the left and to the right when I change it. So if I make a linear change, 5-unit incremental change to mu, it will slide the distribution incrementally 5 units as well. It'll do it exactly the same. So that's a linear shift parameter. So we might think we don't want to add information to the location parameter. Since it is a location parameter, we might be inclined to think, I want a distribution that doesn't inform the location. And flat priors do that. So a prior that doesn't inform the location means this. Location or shift. These are synonyms to me. Invariant. Prior. Now, I wouldn't want to put a location invariant prior on a scale parameter because it doesn't have that property. It's not how we interpret it. But a location parameter, if it's a linear shifting thing, then I might want to think, I want my prior to be the same no matter how I shift it around. If I use the conjugate prior, I'm putting information on the shift. So I'm saying the shift is probably around there. How certain I am, that's my expression of uncertainty about it. So I might think, I don't know anything about the shift. I don't feel good about putting any information on the shift. It makes my life easy. I can do a conjugate analysis, but I'm informing something I don't know anything about. So you might not want to do that. So you might want a prior that looks like this. And I'll use mu, but this is just an arbitrary random variable. We're looking for a prior that has this property. So that's my shift. I'll call it delta. Some shift. So as I shift the distribution, and these pi's are supposed to be the same. This is the hard part of stats, is sometimes my pi's mean exactly the same thing and sometimes they're different. So this is the same function. So I'm looking for a function that does this because since that's a location parameter, I want my prior to be location invariant. And there's only one distribution in the world that does that I can slide back and forth to the left and to the right and you can't tell the difference. And that's the improper uniform. So the only function that does this is the constant function. It's not a probability distribution because it's non-normalizable. So the only function in general for arbitrary, if I pick different shifts, I understand somebody could come up with a distribution for a particular shift and it's the same thing. But I mean for any value that I change it, it's always the same function. Then there's only one function that satisfies this. So the only function satisfying this is the constant function. We haven't asked that this thing be a probability density, we just asked for this property. And so I can have any function at any height just so long as it's not. I guess you could plug in 0, but we're gonna force this thing to be positive. If we place 0 mass somewhere, we can never learn about that area. And so we're not gonna do that. And so my favorite constant number to multiply is 1. So lots of good reasons, but when people just say, oh, I want to do the non-informative analysis, they've got to say in which way they're non-informative. You can't be non-informative about everything simultaneously. And we all know this just from daily life. It's like, I want to say something vague and whatever, and you say something, and you don't even realize what you just said, but it comes back to bite you. It's like, I was trying to not really say anything, but I said the wrong thing anyway. Anytime you open your mouth and you say something, there's some info there. Same thing with priors. There's some info in the flattened prior, but not about locations. So I would like us to not use the word non-informative, but if you're working around analysts that they like this and they're willing to adopt it and they want to write in that way, maybe that's a good thing, in your area to use that terminology. Just as long as we understand, we don't really mean non-informative. Does that answer your question? Why we're looking at this analysis for mu squared? It's fairly arbitrary. It's just meant to show that the transformation on mu squared is not flat. So anyway, that was a very easy, it's very convenient to do this sort of thing. So the flat prior might look like this, proportional to 1, and that's what you'll see most people write. So again, not a probability density. And they're going to operate through Bayes' theorem. So they're really only using Bayes' theorem as a functional construct, telling you what to do. They're not actually using it as though it's a probability distribution, which is different. So pi mu given x1 and sigma squared was equal to, I'm going to just write this thing down. I'm going to normalize it because I know how it's normalized. Minus 1/2, this was x1 minus mu. That's the likelihood function, the way that I wrote it down before, divided by sigma squared times 1. And I happen to go through and normalize everything just because I know what the integrating factor for this function is. That's just something I've learned over 25 years of my life. It's always that thing. And so I can get rid of that because that didn't do anything. And I can spin these around so it looks like it's in the form that you're usually acquainted with. We didn't have to complete the square or anything like that. That only happens because we only have one data point. Later on, we'd probably have to either think about a relationship through the minimal sufficient statistic, and then we can apply the same trick, or we would write down the likelihood in terms of its product form and have some algebra to do. We'll do both exercises. So this is a neat answer right here. So this says, I think mu is in here. It's centered at x1 and has variance sigma squared. So I usually just write down the sigma, but you can annotate however you want. And if I were going to find a confidence interval on all of this, or sorry, an interval, a belief interval on mu. So say we wanted 95% of this mass right here, and I wanted this to add up to 95%. So the Bayesian interval (95% belief), this is what you believe mu to be, is equal to x1 plus or minus 1.96, approximately, it's not exactly that number, times sigma. So for one data point, that's the standard error. And if we had more data points, this would get scaled by n, root n, and this would be the sample average. We'll see that later. I asked you to do it on your homework, so it's a very easy problem. This is the belief interval right here for this. And that's exactly the same interval that if you were taking Stat 101, if they said construct a confidence interval, you would have constructed that confidence interval. So the sample average for one data point is just the one data point, and the standard error with n being 1 is just sigma. So this is an interesting thing. So I recall when I was in Stat 101 that if people said that's the interval where they believe mu to be, the instructor would say that is the wrong interpretation of the confidence interval. The confidence interval is the explanation is it's a random interval that covers the truth some percentage of the time that you state a priori. So it's really a statement about the process and not the analysis, and not a statement about mu. And that always confuses people. They're like, what does it mean in terms of mu? You're saying if I made 100 of these intervals, 95 of them would cover the truth. What does my one interval mean? And nobody ever has a satisfactory answer. They'll say, well, mu's either in the interval or it's not. That's probability 1 or 0. So it's really just the probability of the interval covering. And a reasonably adept student would say, I don't get it. But you get a B and not an A if you do that. This is kind of interesting. The Bayesian says mu's in here. So they use that interpretation for this analysis. This has an interesting symmetry between the data and mu. So this isn't always true that they're the same intervals, but in this case it is. And we used a flat prior too. So turns out to be exactly the same interval because of symmetry. But I could interpret this as the interval where mu lives. In here, 95% belief statement, and it also has an interesting frequentist property. This interval covers 95% of the time if the data is generated actually from a normal distribution. So you can have both interpretations simultaneously. That's optimal coverage and it's a belief statement. So best of both worlds. That's one of my favorite things when two paradigms align. I love when that happens. Usually in analyses you have to choose something. You can't have it all. But this is an analysis where you can have it. Okay, so that's appealing and super easy to do, super easy to interpret, probably pretty easy to explain to somebody. I'm sure most of you are like, well, why be Bayesian? If I could just have the old thing, and you didn't give me anything new, you just gave me an interpretation. I guess that's okay. I'll try to give you more reasons. For this analysis, it's not super compelling. So let's look at the conjugate analysis. So the conjugate analysis. I think that there's a lot of insight here. So pi mu is equal to a normal distribution, mu naught sigma naught squared. So that's my prior. And so let's just do the analysis using that. Question. Sometimes I write sigma squared, sometimes I write sigma. I mean the same thing. So this is going to be equal to, I'll just say proportional to, I think we're used to it now. We'll recognize what the normalizing constants are later. If we know what the normal looks like, it'll be easy to recognize. So again, every distribution we touch, you should know that distribution, know its mean, know its variance, unless I say otherwise. So we're just going to write down the likelihood, e to the minus 1/2 x1 minus mu squared over sigma squared. And now I'm going to write down my prior and multiply against it. So this is going to be the random variable is mu. It's centered at mu naught. And it has variance sigma naught squared. So this is my likelihood. And this is my prior. Of course, there is the question, what's mu naught and what's sigma naught? Now this is kind of fun. If I were just a subjective Bayesian, and I say, oh, I always just encode information that I believe before the analysis, this gives you an opportunity to do that. So if I kind of knew about where I thought mu was, I could anchor it. And if I had some approximate variance, I could plug it in. Of course, that's not super appealing if you don't have any idea. So we need other ways to think about things, so this already has some appeal to it as well. We're going to show that there's a relationship between these two priors. So I'm just going to do the expansion. So I'm going to expand the square on both things, and then I'm going to combine terms. I'm going to identify the quadratic term, and I'll identify the -2 linear term. And we'll essentially be done. So I'm going to combine these, e, and I'm going to have two sums that appear. So this will be my first sum, and then I'll have another sum. So in one step, I'll combine everything into the same exponent, and factorize the -1/2 out. They're on both of them, so I just factorize those out. So this is going to be x1 squared minus mu, I'll say -2 mu x1 plus x1 squared. This is all divided by sigma squared. And this one is going to be mu squared minus mu naught, I'll say mu naught, 2 times that, divided by sigma naught squared, plus mu naught squared over sigma naught squared. So just some expansion of the square. I'll point out, since we've already written this already up to proportionality, there's a bunch of stuff that can be factorized out. In fact, there's two things that I can factorize out of the analysis. This, that's divided by sigma squared right here. Those are constants in this analysis, because we're presuming we know what the variance is. And this, those are constants as well that I had to encode into the analysis to carry out the analysis. So every Bayesian analysis is conditional on their hyperparameters. So I can factorize out that stuff, and I'm just left with, this one's gone. That was wrong. That's the mu squared. So again, just 9th grade algebra. I can't do that stuff. Okay, I think it's right now. So I can throw that away and I still have the mu. So proportional to, and I can write this down, and I'm going to collect mu squared terms, and I'm going to correct.
That mu squared should also have sigma squared.
This one?
No, the other one.
Ah. Okay. Is it right now? So I'm just going to collect the mu squared terms first. So mu squared has a 1 over sigma squared. And there's also one here. And it's the prior variance. And there's a -2 linear term. And if you do this right, you'll always have these two terms. So I've got -2 mu, and you'll notice that I cut the mu in front on both of them. So I did this a little bit less than systematically, because I know I'm looking for that as the variable. So I just didn't spin those around later. Just do it up front. This is going to be x1 over sigma squared plus mu naught over sigma naught squared. Let's find the expectation. So the hard way to do this is to now complete the square. The easy way to do this is to recognize the parameters in the expanded form. So the variance. And this is going to be the posterior mean and variance. So I like to be polite and write down what I've conditioned on and what the random variable is. So the variance for mu, I recognize here. So I'm going to take that and I'm going to invert it. Sigma squared plus 1 over sigma naught squared. Invert. And if you want to simplify that the way that Peter Hoff does in his book, you can do that. I actually prefer it to look like this. So if you want to satisfy your 4th grade teacher and write it as one fraction and not an operator on top of it, you can do that as well. The expectation, x1 given sigma squared, I'm going to identify by looking at this and multiplying by what I just found. So this is going to be x1 over sigma squared plus mu naught over sigma naught squared times the variance that we just found. I really like this expression right here. We'll pick up with this next time, but what I want to point out to you is just two really quick things. This is a weighted average. So I'm averaging together x1 and mu naught, and I'm weighting them with terms inversely proportional to the variance. The inverse of the variance is the precision. And then I have to divide by the normalizing weights to make it a weighted average. So this is just a weighted average, and that's what the answer the Bayesian is giving you, is a weighted average between your a priori beliefs and your data-driven beliefs. So I like that. I want to also point out this thing, sigma naught squared. If that goes to infinity, so the question is how do I pick this? You might be thinking, I don't want to put a lot of certainty around mu naught. I want to make it really big and diffused around mu naught and not overweight that. What you'll find out is this thing goes to 0. And this thing also goes to 0. That sigma squared will cancel that. And the expectation of mu given x1 and sigma squared will go to x1. And that was the analysis we got under the flat prior. And so here's a way to think about the conjugate prior, is it's a limit, or here's a way to think about the flat prior. It's a limit of the conjugate prior. So if you want to play this abstraction game in your mind, think about just making mu naught bigger and bigger and bigger and bigger and less information on mu naught. And if you want to work with a proper prior, if working with an improper prior really bothers you, use a proper prior with extremely diffused variance. And then make it even bigger, and make it even bigger. And eventually, we will agree. So this is the limit of that thought process. So the flat prior is a limit of conjugate proper priors, but it's improper at the end of the day because it doesn't normalize. I probably need to define improper prior on the board for you, but I'll do that next time. And then I think we'll switch over and talk about the variance. So let's just come back to this answer next time, talk about it for a few more minutes. Maybe look at what happens as we accumulate a little bit more data in this analysis. This thing would still, if we ended up using the limit sigma naught goes to infinity, this would converge to x bar, the mean, which is the typical answer. I kind of like this because it gives me some dials that I get to play around with. I can take this dial and spin it around infinitely and turn it into the improper thing. That gives me an optimal frequentist answer. Or if I needed to encode information that I have, it gives me placeholders for that as well. So let's come back, say that again, and then move on to the variance. And so I will ask the question at the beginning of that analysis is what is the conjugate prior for the variance? Anybody want to say right before we go? The variance, sigma squared. That's the next analysis. You want to do it, Anna? Inverse gamma. Good for you. So a lot of us don't like to talk about inverse distributions. So we're going to play a different game, and I'm going to invert the parameters so that we can use a gamma. I'll show you what is done there, but it's the common thing. Those Bayesians will do that. Lots more discussion in front of us. Have a great 3-day weekend, and I will see you not on Tuesday, no review. I'll see you in class on Wednesday, and then we'll do a review the following week. Thanks, you guys.
For homework, do you want us to turn it in paper or online? Or?
I do like it.
All right, I have paper.